All right. Good morning, everyone. I will be your host this morning. My name is Mike Jacobs with Long Building Technologies. Throwing everyone for a loop this morning. We were having some scheduling and technical difficulties this morning, so I'm going to play a clip that was pre-recorded over Swegon's demand control ventilation presentation. Mike Woolsey, the Swegon Business Development Manager, will be presenting this one. And hope you guys enjoy and talk to you after I play this quick clip.
Okay. You may have seen this chart from us before. So this isn't meant to say that the other manufacturers do it wrong. This is actually meant to describe to you what Swegon is capable of. Swegon offers both or not both, but CAV, VAV, and DCV systems. So first up there, we see CAV, which is the constant volume solution. Oops, didn't want to do that. There's me. There we go. Constant air volume solutions. They're the simplest. There's plenty of projects out there. You hear talk from Swegon about Passive House all the time. Most Passive House projects in North America so far have been constant air volume, and they're near zero. So you can make a building very energy efficient with constant air volume. We're not trying to say that constant air volume should never be used. Even the most energy efficient VAV building might have areas where constant air volume makes more sense. So we're careful not to say that this is bad. We're just trying to point out that it is the simplest system. It's often viewed as the least expensive option, but that's usually a first cost discussion. It will have the highest life cycle cost because, according to this graph, no matter how much airflow you actually need, you're always spending the maximum amount of energy driving the fans at their maximum, even if the building's empty. Next up, we have variable air volume, very common in North America, less common in Europe. It is the ability of our ventilation system to be controlled by room temperature. And that is, as the room temperature departs from set point, we can add more cool air to cool off the room to meet the thermostat need. VAV systems typically will use pressure control. And in our experience outside of Swegon, we see that pressure control is often maybe oversimplified. We'll talk about that today. We also know that because of the temperature control, that black line on the chart there shows us that as we slow down the fans, thanks to the fan laws, the affinity laws, we save multiples in energy use. We use the air handler unit fans to control the pressure, of course, and we do expect a lower life cycle cost than constant air volume. You can read in many, many places that you should expect that over a year, you should expect a VAV system to be about 70% less energy, consume 70% less energy than a constant air volume system. Then you get a little extra bump from demand controlled ventilation, which is very, very similar to VAV, defined here by Swegon as airflow that's controlled by temperature and CO2 or occupancy or some other measure. So it's not just controlling temperature and comfort, but it's controlling more of the holistic indoor environmental quality. So that if the temperature is okay, but the CO2 level's high, we could provide more airflow. But if the temperature is satisfied and the CO2 levels are low, we might be actually be able to lower the airflow even more. So that's why the pink line shown there is below the VAV line. And we expect demand control ventilation to have the overall lowest life cycle cost. That's the concept. Here's some proof. Several years ago, we worked with a colleague, as we always do. Colleague wanted to build a building to make use of Swegon's demand control ventilation system. So we designed the system, and then we were allowed to measure the airflow once an hour automatically, once an hour, every hour for a year to see what that sort of a system was capable of. So we learned a few things in doing so. The first point there is that we never ever needed more than 76% of the design airflow. That's exactly what you should expect out of a DCV system. There could be an argument that maybe they oversized the system. What we don't know is maybe they did oversize the system for a future expansion or something. But I think there's an argument here that this supports the idea of diversity in variable air volume in DCV systems. And we hear engineers talk about diversity numbers of 80% or 75%. And that is, they're saying that although if the building were fully occupied all the time and at maximum load all the time, they would need 100% of the airflow. But because it's a variable air volume system, they're assuming they'll never need more than 80% or 80% diversity. I think there's some support for that in this research that we did. The second point is that most of the time, like 80% of the time, we needed less than half of the design airflow. So the result is you can see that blue line there shows how our electrical consumption varied right along with the ventilation rate, as you would expect. Pretty easy to calculate with specific power. But the idea is that we saved a lot of energy by being able to turn down the system. Not really news to us and our customers here in North America, except for one group. We find ourselves here at Swegon doing lots of residential work, that is multifamily residential. Sometimes our projects involve buildings that don't look at ASHRAE 90.1, but they look at ASHRAE 90.2, which doesn't really have the same requirements. So they're really not used to applying demand control ventilation. So let's get a refresher here. This is a nice animation that shows us what a typical building is actually like during a typical day and why it is that we don't need all full 100% airflow all the time. So we're delivering air to meet the variable needs. So we see people, the little green shadowy figures there. You can see that during the day, people move around. They go to meetings on the other side of the building. The building has the sun move around it, and all sorts of things are continuously changing. So we want to have a system that provides variable airflow, but at constant pressure, so that we can always get air where it needs to go. Lots of competitors are already doing that. This isn't new. What is new is that Swegon believes that we're adding value by providing a complete package of system components, as opposed to just one piece of the system, that as a system can deliver greater efficiency and greater precision, resulting in even better energy reduction, resulting in better or lower emissions and better comfort. I already mentioned ASHRAE 90.1. Depending on where you live and what your jurisdiction has decided for their local building code, if they've adopted the language of standard 90.1, then it's pretty likely, depending on the building size, of course, that you will need to apply demand control ventilation anyway. So it doesn't matter how nice of an idea Swegon thinks it is. It's possible that you're just flat out required to have DCV in your building to meet ASHRAE 90.1. We could spend an hour talking about ASHRAE 90.1. We're not going to. Let me just say that if you look at the requirements of 90.1 from this chart, you can determine whether or not your building needs demand control ventilation. If you're new to this whole thing and you are going to meet with a client and you want to talk about this sort of thing, and we're here to help you, we can certainly answer your questions or even participate in discussions. So we've got the demand control ventilation demanded by code in a lot of places. Let's get back to the need for demand control ventilation. What we're showing here are two things. One is we've got the time of day across the top. So you can see how a typical single person office with a chill beam in it first has no occupants at night. So very minimal load, we'll call it. And then first thing in the morning, the sun's shining through the window. The load increases, the building is on, so air starts to flow. That's what the red line is showing us. Then as the occupant starts to work and the sun continues to shine, the temperature goes up and the need for more cool air goes up. So we provide more air, as the sloped red line tells us. And then we get to a peak late in the afternoon. The occupants has a meeting with some extra people. Peak load, peak airflow by design, not at 100% airflow possible necessarily, but at some preset maximum that's controlled by some sort of control mechanism, some sort of damper.
All right. Well, I appreciate everyone working with me through the technical difficulties this morning. Um, we're going to end it there, but wanted to put up the prizes this week. We have a Topgolf $100 gift card, a Bose Bluetooth speaker, and a funny desk sign. Please join in next week when Ryan Nabalski is going to present with Caitlin Sporter, Casper, redefining safe and healthy indoor spaces. Well, that concludes our coffee break. I appreciate everyone's time this morning and have a great rest of your week. Thanks.